Alright, hello physics fundamentalists. Today we are doing LR circuits, the last new content of Unit 3 on magnetic fields and magnetic forces. As you know, there is a test later this week. Last week we talked a lot about magnetic flux and Faraday's law, and the idea was that a changing flux through a loop caused a voltage that would cause a current. Okay? And so, to get today starting, let's go ahead and look at a problem that reminds us about how Faraday's law works. Okay, so in this problem we say a permanent magnet is moved towards a 320 turn solenoid such that the magnetic field inside the solenoid increases from 0 to 50 Tesla. So the change in the magnetic field is 0.50 Tesla. That's very important because remember, it's not the size of the magnetic but the amount that the magnetic field changes that induces a voltage in 0.75 seconds. So our time here is 0.75 seconds. The radius of the solenoid is 0.035 meters. So that's this. The ends of the solenoid are connected in series with a light bulb. What EMF is induced during this time interval? Well, recall that EMF is electromotive force, which is a bad name. It is actually a voltage. So we're solving here for this, but this is actually the voltage that's caused by the changing magnetic flux. Now, you might want to keep in mind, magnetic flux is the integral of the magnetic field dotted with the surface area vector over a surface. So we're looking at this surface here, and essentially we're going to take the change in flux over the change in time, multiply it by n, the number of loops in that solenoid. So here are, and they're just, the minus sign, you may remember from Friday, has to do with the direction of the induced current, or the induced voltage. It's to try to oppose the change in the magnetic field. So you can figure out what direction the current is going to be going through. It'll be going through so as to create a magnetic field that's pointing the opposite way as the direction in the increase. So let's forget about the minus because we're just looking for the magnitude right now. It would be n times the change in magnetic flux, so that's going to be our change in magnetic field times that surface area of that surface. Okay, if the area is not changing, we don't have to put on another term for that, all divided by the change in time. So in this case, it would be 320 turns times 0.50 Tesla times, and then the surface area would be pi r squared, so it would be pi times 0.035 meters squared, all divided by the amount of time it takes for this to happen, which would be 0.75 seconds. Okay, and then you go ahead and you plug in all those numbers and you should get something right around 0.82 volts. All right, now I have given you a homework problem on this. This is in the practice problem I just showed you, it was the magnetic field that was changing. In this problem, it's going to be the radius itself that's changing. It says a balloon has an initial radius of 0.075 meters. A circle is painted on the balloon using silver metal paint. So we're imagining it's kind of like this. Here is our balloon. We've got stretchy, stretchy metal paint around it, and we're blowing up the balloon, and as the balloon blows up, it can get bigger or smaller. It says, when the paint dries, the circle is a very good electrical conductor. When the balloon is oriented such that a 1.5 Tesla magnetic field is oriented perpendicular to the plane of the circle. So it's like this. There's the plane of the circle, and my B of 1.5 Tesla is pointing perpendicular. Air is blown into the balloon so that it expands uniformly. The circle expands to a radius of 0.125 meters in 1.5 seconds. Determine the induced EMF for this silver circle during this period of expansion. Now, when I read this problem first, I was thinking, well, golly, it seems a little tricky because as I continue to blow air in there, the more air I blow, the less this radius is changing per unit time. Okay, so I want you to sort of squint, forget about that problem, and really just focus on the idea of this radius is changing. That means that the area is changing. So when you're trying to find the induced EMF doing this homework problem, I would want you to do it sort of, it's the change in the flux over the change in the time, and essentially that could be the change in B times the sorry, let me put it this way. It's going to be the magnetic field, which is not changing, times the change in the area over the change in the time. And so the change in the area, you can find that just by going ahead and taking your pi r final squared minus your pi r initial squared. Okay, and I realize if you wanted to do this problem perfectly correctly, you would find an EMF that's not constant, because if you're blowing in the same amount of air every second, for instance, your rate that circle is getting bigger is not steady over time. But let's not get hung up on that point when you do your homework problem. Okay, now you'll hopefully remember from Friday that Lenz's law tells us about the direction of induced voltages, and sort of the anthropomorphic way of putting this is that currents don't like change, right? The desire of a thermostat is to keep the temperature the same, and the desire of a loop of wire like this is to keep the magnetic flux in its belly the same. And so when that magnetic flux is increasing, it will provide an induced magnetic field that will oppose that change. And so this tells us about the direction of the magnetic field that's induced. In this problem, it says we are going to try to remember what we learned about Lenz's law on Friday. We did this in a couple different, we split this into a couple different problems on Friday, but here we have it all in one problem. You are looking at the direction of the magnetic field in a specific region as shown. A square metal loop is moving from the left to the right at a constant speed. Which one of the graphs below shows the behavior of the current, if any, in the loop as the time passes? Okay, now recall that the induced voltage is going to be related to the change in flux per unit time. So as this box is moving into the magnetic field, it's going to have a changing flux. Once this box is all the way into the magnetic field, however, the amount of magnetic field times the surface area is constant for a while, and so this voltage drops to 0. And then as you move out, once again, the magnet doesn't like any change, the loop doesn't like any changes in the status quo. So it will induce a current that will keep the magnetic field inside of it pointing as close to the same direction as it was before. Okay? So effectively, as this loop is entering on one side, it's going to have a magnetic field induced that's pointing out of the page. So the I would be like this. Here, this is the I direction of the current. Here the current would be 0. And then as I go out of the magnetic field, the magnetic flux is decreasing. So I want to induce a magnetic field into the page to keep things as much like they were as possible. And so I'm going to have a current that goes that way. Okay, so the current is going one way, 0 going the other way. And I believe we're going to have something like this. And the reason is that the change in flux per unit time is the same as long as our square is going in and out. All right, now the last idea that we introduced on Friday was flux and inductance. And the idea here was that we have a new property of a loop that has to do with the ratio of the induced of the flux to the current. And this ratio of flux to current is going to help us to figure out how much essentially magnetic energy is going to be stored in that object. And we did a specific example where we found out that the inductance per unit length for a solenoid was this. It depended on the winding squared and the cross-sectional surface area, and that would give us L. And remember, L has units of henries, which, you know, this can all get very weird because essentially it's Webers per amp, but you can put it in other terms too. And you'll remember on Friday we did this problem where we have two solenoids A and B. They have the same length, same cross-sectional surface area. The solenoid B has 3 times the number of turns per unit length. And so when you compare their self-inductances, that L, you would have that LB is going to be essentially 9 times that of A because you have that N squared, so it would be 3 squared. Now today we're going to press on. We talked about this inductance. Okay? Now we can use that quantity to try to quantify how much Faraday's law is going to act on an individual component. So what do I mean by that? I mean, if we have a current going through a solenoid, for instance, here's my prop solenoid, there will be a magnetic field in the center. And a changing magnetic field in the center will mean that if I, for instance, change the current through there will be an induced voltage that will oppose that change in current. Now let me just show you how this works. We have 2 rules. We've got a definition of our inductance, and we have a rule, Faraday's law, for our induced voltage or induced EMF. Now, if we put these together, we can find a new rule that relates for a particular inductor how the induced voltage from its own current will relate to the current going through it. Okay, so if I define my inductance this way, I can redefine my flux in terms of the inductance. Okay, so just rewriting this rule in terms of a delta B equals, it would be phi B, this would be the magnetic flux. Magnetic flux equals L times I divided by N. And then if I take the change, how is that magnetic flux changing in time? If I have an object whose inductance is a constant, it's a property of the device, then the N, the number of loops in that coil, is not going to be changing. The L is not going to be changing, and so the entire change in the flux per unit time is just going to be L over N times di dt. Okay, so we're taking the derivative, time derivative of both sides of this expression. Now, once I have that, I can stick this into my Faraday's law. And so what I get is that my EMF is equal to minus N times, and now I'm going to put this in for my change in flux per unit time. It's going to be L over N di dt. Notice that I have an N on top and N on bottom, so those cancel out. And so what I find is that the induced voltage from a changing current in an inductor is equal to minus L times di dt. So I am going to be able to treat this like I would treat a resistor or something like that in a Kirchoff's law scenario where I can put this into a circuit. But notice that it only gives me a induced voltage when my current is changing. If I get to a point where my current is not changing, where I reach a steady state and all the currents have kind of settled down within my circuit, this is going to act just like a wire. The induced voltage is just going to drop to 0. So let's see if we can think our way around this. All right, so the circuit that we're really interested in today is called the RL circuit. And what is it? Well, resistors, we already know how to draw them in a circuit diagram. So here's our battery, our voltage source. Here's our resistor. And now, whenever we have an inductor, this is something that stores magnetic energy, we're going to draw it sort of like this. It's supposed to look like a loop. Right? Looks a little bit like it. You've got a loop of wire going around a core. All right. Now, what I'm going to claim here is that if we were going to go ahead and connect this circuit up, what would happen is that because this would resist the changing current, as soon as you turn this on, you're initially not going to get a current, just like if you just put a resistor in there, you'd go blam, 0 current, full current, virtually almost instantly. But when you put that inductor in there, what happens is that instead of instantly turning on and getting your full current, you have a current that takes some time to reach its maximum. And that maximum current is still just going to be related to V equals IR. So it's just going to be, your maximum would just be the voltage divided by the resistance. Okay, so the amount of time it takes to get there, we relate to the inductance of the coil and the resistance of the resistor. And the idea here is that the bigger the inductance, the more magnetic energy it takes to essentially charge this up with magnetic energy, get it to its final magnetic energy, before you can start simply treating it as a wire, and then all of the energy coming out of the battery is going to it's going to be used in dissipating energy through that resistor. Now, just to make sure we understand where this is all coming from, we have now two different Kirchoff, two different rules for what the voltage across devices looks like in this problem. We've got our V equals IR, and I'm going to write it in a little bit of a weird way here, but we also have our V equals minus just let's make sure that we show it, minus L di dt, minus L di dt. And really, if you were going to be consistent about the minuses, we'd put a minus here as well, because that voltage opposes the direction of the applied voltage, right? So if remember, we said back in the day, if you add the voltages around any loop in a circuit, you should add up to 0, because the amount of that the energy that you're gaining is going to be lost or stored in other elements. So in this case, we would have, let me draw the circuit. This is the rising current circuit, where you have a battery and a resistor and an inductor. And that's the whole circuit. And the Kirchoff loop for the loop rule for this would be 0. We're going to sum all the way around here and get 0. And let's go around this way. 0 equals the voltage of the battery minus the voltage across the resistor minus the voltage induced by the inductor. Now, you could also have this other circuit where you would have dropping current. Your current would be getting less, and essentially at that point your inductor would want to keep the current going in the same direction as it was initially going, but it would be pushed against now by the resistor. So in this case, the direction, because your current is not rising, it would be dropping. The direction, instead of going against the current, it would go with the current. So I would have 0, and then this loop would now just be a resistor and an inductor, and we don't have a battery source anymore. And we would still have the minus IR, our loop is still going this way. So it would be minus IR, and then it would be plus L di dt. Now, I want you to notice these are differential equations that I hesitate to say you could solve, but one could solve. In fact, I will give you the solutions to these differential equations. The solutions are that the current in the first case looks like this. It looks like something that starts low, and as you turn it on, it rises and rises and rises. At the end, it will reach the current that you would get if you just had the resistor and the battery and the inductor weren't there. So this is this transient term that is going down to 0, and how long it takes to get there depends on the inductance of the inductor and the resistance of the resistor. So if you put in that inductance in henries and that resistance in ohms, you should ultimately get something that's in terms of seconds. Same idea over here, except now the inductor is the thing that's providing the energy to keep the current going, and then that current is dying off. And how long it takes to die off to its zero value depends on L over R, because the bigger the L is, the more magnetic energy it will store. The bigger the R is, the less current per time that's going to flow through there. Okay, so to walk ourselves through an example here, what happens in a situation like this where I have an inductor and a resistor and an inductor, and just a resistor? Well, if I close this wire, initially what happens is that the inductor acts like a broken wire, and so you just get current through the middle pipe. But at the end of the day, once this current has reached its final value, these inductors now just look like a wire because the transient term has died off here. They are sitting here storing some magnetic energy eventually, but the resistance of each one of these resistors is still going to add together like 3 resistors in parallel. And if you wanted to look at the equivalent resistance of this circuit, it ultimately would be the same as, doing the 1 over R equivalent is, 1 over R plus 1 over R plus 1 over R. And you'd still get that same equivalent resistance you would get for three resistors in parallel. Now, I think it's going to be helpful. Whoops. All right, sorry about that. And not another homework example. No, this is just a homework example. Okay, so it says a 150 ohm resistor and an 80 millihenry inductor. So L is the inductance. So this would be 0.80 times 10 to the minus 3 henries are used in an LR circuit. If the initial current in the circuit is 2 amps when the switch is thrown that allows the current in the circuit to decay, at what time will the current be 1 amp? Okay, so the initial, if this is a decaying current, you have equations for the decaying current and for the rising current. This is a decaying current. Your initial current is 2 amps. Your final current is 1 amp. And you want to find the time. So that's this. Well, keep in mind you can already solve for this time constant, this L over R. So that TL is L over R. Taking this 0.80 times 10 to the minus 3 divided by 150, this should give you some small amount of time. Okay? Now, if we want to use this where we start out with the presumption that the current at some time later than time equals 0 equals the initial current times e to the minus t over tau, how would I go ahead and solve this equation? Well, you're going to have to go back and remember how to use logarithms. Now remember, if you have e to the x equals some number, a, if you take the natural log of each side, this brings down the exponent here such that x equals log of a. So if a is just a number, I can put in the natural log of that number into my calculator and get out the exponent. So that's what I'm going to have to do here. I would have I over I naught equals e to the minus t over tau. And then I'm going to have to take the natural log of both sides. And what that does for me is that gives me a minus t over tau equals, so I've taken down the exponent. Notice that I need to keep my minus sign around here, equals log of I over I naught. Okay, so I think I've set this up well enough for you that you are going to be able to go ahead and solve for that t because everything else is here. Now, there is one more thing I want to discuss a little bit in this video. I have sort of hinted at this earlier, but inductors are a little bit different from capacitors and resistors. Capacitors store energy in the form of electrostatic charge. So you can just put that charge on a capacitor, walk away, and and disconnect it from a circuit and everything, and that capacitor can continue to store that electrical charge. A resistor, on the other hand, stores no electrical charge. The capacitor stores the electrical charge, and the capacitor also stores electrical energy. A resistor, on the other hand, does not store any energy, it just dissipates energy. So the rate at which it dissipates energy is the power is I times R, and that gives you the power that's being dissipated through that resistor. It's getting hot, or letting off light if it's a light bulb or something like that, at a rate in watts, which is joules over seconds. Now, what's interesting is that a inductor also has some relationship to energy in the circuit, but it's not dissipating energy. It's just holding on to some energy related to the amount of magnetic field that it generates. And I think the easiest way to get to this is to start out with the Kirchoff's law loop rule for a charging system. If you multiply each side by I, you can recognize that this is the amount of power that's being delivered by the battery. This is the amount of power that's being dissipated by the resistor. So this is battery. This is the resistor. And our extra piece here is the amount of energy that's being put into our inductor. And notice as we are reaching a steady state, as this current is changing, if the current is getting smaller, if the change of current is getting smaller, it's not sucking up more and more and more energy. Eventually it just reaches some final value. And that final value is just going to be whatever current it sits at. So it starts at zero energy. Because it has that magnetic field in its belly, that magnetic field density, if you integrate it over space, has some energy. And if we want to look at this and say, okay, this is an amount of energy that's being spent by the battery, this is the amount of energy that's being put into the inductor per unit time, this is the amount of energy that's being put into the resistor per unit time. If I look at this, the amount of energy that's being put into the inductor per unit time is equal to L times I times di dt. So this is a rate, this is a rate, and I'm going to do an extremely sloppy physicist thing and say that the differential amount of energy that I'm adding into that inductor per each extra bit of current that I'm putting in is going to be this. I sort of divided out multiplied each side by dt. Now, if I integrate from zero energy to that final energy, it essentially is going to be integrating from zero current to whatever my final current is. And so I get that UB, the amount of energy stored in the magnetic field of that inductor, is going to equal, well, you can just do the integral here. It's going to be 1/2 Li squared, and then subtracting off the bottom is going to be 0. Okay, so this is the amount of energy stored by an inductor, 1/2 Li squared. And you can compare that to the energy of a capacitor, which you may remember was 1/2 CV squared. All right, so let's take a look at another of your homework problems. It says a coil is connected in series with a 10 kiloamp resistor. So R equals 10 times 10 to the 3, kilo ohm resistor. Okay, an ideal 50-volt battery, or maybe I should put it in this terms of a squiggly E. Okay, so 50 volt is applied across the two devices, and the current reaches a value of 0.2 milliamps after 5 milliseconds. Okay, so the current, that would be I, is 2 times 10 to the minus 3 amps after a time of t equals 5 times 10 to the minus 3 seconds. All right, then it says find the inductance of the coil and then how much energy is stored in the coil at this same moment. Okay, so part A is asking find the inductance of the coil. Now, it might not be obvious how you would do this, but essentially you know the current, you know the resistance. This is a rising current, is a current that's getting bigger. It's getting towards its final value of V over R, epsilon over R, or squiggly E, eta, whatever. So in this problem, essentially what you're going to do is this. You're going to stick in all your values here. You're going to solve for your time constant and realize that your time constant equals L over R, and then solve for L. To make that a little more concrete, let me take this, I'm just going to rearrange it a little bit by multiplying each side by R over eta. So it would be IR over eta equals 1 minus E T over TL. Okay, so I'm just taking this and I'm multiplying out some stuff. This is going to let me rearrange my sides a little bit. So this would let me add e to the stuff on both sides and subtract off IR over eta on both sides. And this would give me e to the minus t over tau equals 1 minus IR over voltage. Okay, so I hope you see what I'm going to do now. What I'm going to do is I'm going to take the natural log of both sides. And that would give me minus t over tau is the natural log of 1 minus I over R over eta. Okay, so I'm going to let you go do the rest of that, And once you find out what tau is, you're going to use tau is equal to L over R and use that to solve for L. That will give you the inductance of the coil. Then for part B, it asks how much energy is stored in the coil at this same moment. Well, once you have L, you can use 1/2 Li squared to get some amount of energy. And remember, our energy units are joules. Okay, so you're going to use part A to find L, use that L, and then use the I that they've given you to find out how much energy at that instant is being stored in the magnetic field of the inductor. Okay, here's the last homework problem that I gave you on this. Let's just read it and make sure that we're feeling okay about it. It says, at time equals 0, a battery is connected to a series arrangement to a resistor and an inductor. Okay, so this is our standard old RL circuit in series to a resistor and an inductor. Okay, so all of our RL circuit stuff that I've given you will apply here. It says if the inductive time constant is 37 milliseconds. Okay, so that's this. 37 times 10 to the minus 3 seconds. At what time is the rate at which energy is dissipated in the resistor equal to the rate at which energy is stored in the inductor's magnetic field? Okay, so remember, this equation tells us that the voltage times the current coming out of the battery is equal to, so this is the amount of energy that's leaving our battery is equal to the amount of energy that's being put into our inductor plus the amount of energy that's being dissipated by our resistor. All right? So in this case, essentially it's saying at what time, so you're going to be solving for t, is this term equal to that term? So you're saying essentially Li di dt equals I squared times R. Okay? And so you can divide off an I from both sides. In fact, I'm going to help you one more step. It says TL is L over R, right? So here we have di dt equals L over R times I. This L over R is just that inductive time constant. And what you can do now is go ahead and use this. Okay, so you know how to take the derivative of that. You can put that in this side. You know how to just put that I directly in here. And what are you going to be solving for? You're going to be solving for t. So essentially what you need to do is isolate all the terms that have e to the minus t over tau, and then take the log of both sides, and then you should get something with a t on it. Okay, so I know we've done a lot of new stuff today. Please give a shot at these homework problems. On Wednesday, we're going to be reviewing for our test, and then on Friday, we will take our Unit 3 test. So what have we learned today? We've learned that the inductance, L, quantifies the voltage that a loop generates as the current changes through it. Of course, L is the ratio of the magnetic flux to the amount of current going through a device that generates a magnetic field. Then the other thing that we've talked about today is what happens when you put an inductor in series with a resistor. It takes time for the current to reach its final value. It also takes time for the current to shut off. Then finally, the inductors are able to generate currents because they store magnetic energy. So that's why they can act almost like a little battery for just a little bit of time after, if you remove the voltage source, because of Lenz's law. They want to keep the current going in the same way that the current was going when the external voltage source was removed. Okay, so thank you for hanging in there with me in this video, and good luck on your homework.